I was looking at my news feed this morning, and it's a barrage. Climate crisis, emissions targets, BPM levels.
It's everywhere.
It's everywhere. It's in our politics, our economy, even, the ads for our laundry detergent. But I had this moment where I stopped and I realized if someone actually backed me into a corner and asked, okay, but how does the machine actually work?
Right. The nuts and bolts.
Yeah, the nuts and bolts, I'm not sure I could give them a solid answer.
Well, you're not alone in that. I think it's a paradox of modern life, really. Climate change has become such a massive cultural buzzword that we've almost stopped hearing the science underneath it. We debate the policy, we argue about the solutions, but we've sort of lost sight of the actual mechanics.
That's exactly it. We know the planet is getting hotter, we know it's bad, but the actual engineering of it, why does a change of just a few degrees matter so much?
Yeah.
Or how can a scientist possibly tell me what the temperature was in Antarctica 800,000 years ago? Because honestly, that sounds a little bit like magic.
It does sound like magic. But as we're going to find out today, it's actually just incredibly clever detective work. And that's really the goal of this deep dive. We are stripping away the politics, the shouting matches, the headlines. We're going to look strictly at the machinery of Earth.
And for this, we're using the DK Eyewitness Climate Change Guide as our roadmap today. And I have to say, going through the source material was a bit of a revelation for me. It's not a manifesto or a political tract.
Yeah.
It's an owner's manual for the planet.
That's a great way to put it.
It covers everything from, molecular chemistry all the way up to satellite data.
It's a fantastic resource because it visualizes the invisible. And that's our mission today, to see the invisible. We aren't just talking about global warming. We are investigating a complex, self-regulating system, a life support system that is, well, currently drifting out of balance.
So let's start at the absolute beginning. The default state of the universe is pretty hostile, right? It's either freezing cold or it's burning hot. So why isn't Earth a frozen ball of ice?
Yeah.
Or a burning hellscape?
The Goldilocks question.
Yeah.
Why is the purge just right? And to answer that, we have to talk about the greenhouse blanket. Now, I know greenhouse effect is usually used as a scary term, but we need to reclaim it for a second.
Right, because without it, we wouldn't be having this conversation at all.
We wouldn't be here, period. But the source material makes a really stark point to illustrate this. If Earth didn't have an atmosphere acting as this insulating blanket, the average global temperature wouldn't be the comfortable 57 degrees Fahrenheit, that's about 14 degrees Celsius, that we all enjoy.
The temperature that allows for liquid water and life as we know it. So what would it be?
It would plummet. We're talking 0 degrees Fahrenheit, minus 18 Celsius. The entire planet would be a frozen, lifeless rock just spinning in the dark.
Wow. So step one in understanding this whole system. The greenhouse effect is actually the hero of the story. Or it was originally.
Absolutely. Think of it like a down comforter on a cold winter night. You need that comforter to trap your body heat so you don't freeze. The problem we're facing now isn't the existence of the comforter.
It's that we're piling on more blankets.
Exactly. It's like we are throwing on 3 or 4 heavy wool blankets on top of it in the middle of July.
And to really visualize this, the book uses something I love, comparative planetology. It looks at our neighbors, the moon and Venus. It's like a real estate tour of the solar system. And the other houses are just nightmares.
It's a perfect way to isolate the variable, Look at the moon. It's roughly the same distance from the sun as we are. It gets pretty much the same amount of sunlight. But the key difference...
No atmosphere.
No atmosphere. No bother.
So when the sun hits it, it bakes. But the second the sun goes down...
Poof. The heat vanishes instantly into space. It swings from boiling to freezing in a heartbeat. There is absolutely no regulation.
And then you have the other extreme. You have Venus.
Yeah.
The ultimate cautionary tale.
Venus is what happens when the greenhouse effect goes completely rogue. Venus has this thick, crushing atmosphere, and it's almost all carbon dioxide.
Right.
Because of that, the surface temperature is over 930 degrees Fahrenheit. That is 500 degrees Celsius.
That's hot enough to melt lead. That's just, I can't even comprehend that. And the interesting thing I picked up from the reading is that Venus might have actually been like Earth once. It could have had oceans, but it had what they call a runaway effect.
That's the leading theory, yes. As it got hotter, for whatever reason, the water ocean started to evaporate. Now, water vapor is a greenhouse gas itself.
Although that made it even hotter.
Exactly, which evaporated more water, which made it hotter still. It's a feedback loop. Eventually, the hydrogen from the water was stripped away by the solar wind and escaped into space. The oceans were lost forever, and all that was left was this suffocating, heavy blanket of CO2.
So when we talk about climate change on Earth, we are basically just asking,
Yeah.
where do we sit on the scale between a frozen moon and a melting Venus?
Precisely. We are trying to stay in that incredibly narrow habitable zone where water can be liquid and life is possible.
Okay, let's get into the physics of this. Because blanket is a useful metaphor, but it's not literally a wool blanket wrapped around the stratosphere. The source material gets into the specific wavelengths here. It's all a frequency game.
It is, and this is the part that usually gets skipped in the headline version of the story. It all comes down to a case of mistaken identity by the atmosphere.
Okay.
The sun sends us energy, mostly in the form of visible light. This is what physicists call shortwave radiation. It's punchy. It's high-energy stuff.
And our atmosphere, which is mostly nitrogen and oxygen, is basically transparent to that shortwave energy, right? It just passes right through. It's like a ghost passing through a wall.
Precisely. That sunlight comes in, it hits the asphalt, it hits the oceans, the trees, the earth absorbs it and warms up. But here is the universal law of physics. Anything that has heat has to radiate energy.
You have to give it off.
It has to give it off.
Right.
But the Earth isn't a star. It's not hot enough to glow with visible light. So it radiates that energy back out as infrared heat.
Which is long-wave radiation, a less energetic form.
Yes. And this is where the trap snaps shut. Oxygen and nitrogen, they let the shortwave sunlight in. No problem. They let the ghost in the front door. But CO2, methane, water vapor, their molecular structure is completely different. They are opaque to that outgoing long-wave radiation.
I loved the diagram in the DK book for this. It showed the CO2 molecule actually vibrating when the heat hits it.
That's exactly what happens. Think of a CO2 molecule like a little tuning fork. The long-wave heat energy leaving the Earth hits it, and it just resonates. It starts to vibrate like crazy.
So it absorbs that energy.
It absorbs that energy, holds onto it for a split second, and then it re-radiates it. But, and this is the key, it doesn't just shoot it off into space. It shoots it out in a random direction. Often, that direction is right back down at the ground.
So it's essentially catching the heat on its way out the door and just throwing it back into the room.
Over and over and over again, billions of times a second all over the atmosphere. That is the greenhouse effect. It's not trapping air, it's recycling heat energy.
So who are the usual suspects here? We always hear about carbon dioxide, CO2, but it's not alone, right? There are others in the mix.
There are several key players. Water vapor, H2O, is actually the most abundant greenhouse gas in the atmosphere. Then you have methane, which is CH4, nitrous oxide, N2O, and even ozone, O3.
Okay, so here's where it gets interesting and maybe a little confusing for people.
Yeah.
If water vapor is so abundant, and I read that methane is actually way more potent molecule for molecule at trapping heat, why does CO2 get all the blame? Why is carbon the villain in every single news story?
That's a crucial distinction to make, and it comes down to two things: quantity and longevity. Let's start with water vapor. It's abundant, yes, but it cycles really fast. It evaporates, it forms clouds, and it rains out in a matter of days.
It's a transient gas.
Exactly. It responds to temperature, but it doesn't drive it over the long term. But CO2 is the forever chemical of the atmosphere.
Yeah.
Once we put it up there from burning fossil fuels, a significant portion of it stays for centuries, even thousands of years.
So CO2 is like the control knob. It sets the baseline temperature, and then water vapor just amplifies the effect.
You've nailed it. CO2 is the thermostat. And while methane is incredibly potent, the source says it's about 25 to 80 times more effective at trapping heat than CO2 over different timescales. There is simply so much more CO2 being emitted. It's the heavy lifter just by sheer mass.
Okay, so we've established the mechanism. Sunlight in, heat trapped by these vibrating molecules, Earth stays warm enough for us. But the Earth has been doing this for billions of years. So why is it all changing now? This has to bring us to the engine of life, the carbon cycle.
The carbon cycle. And you can think of this as the planet breathing.
Literally breathing. I mean, the diagrams make it look like a circulatory system.
In a way, yes. In the natural balance cycle, you have photosynthesis. Trees, plants, marine plankton, they are pulling CO2 out of the air to build their bodies. They turn it into sugar, wood, leaves, stems. That's the planet's inhale.
And then the exhale is respiration.
Right. Animals like us eat the plants, or the plants themselves die and decay. That carbon is then released back into the atmosphere as CO2 when we breathe or when microbes decompose the organic matter. It's a balanced loop. Inhale, exhale, net zero, essentially, over time.
But carbon doesn't just stay in the air or in living things. It gets stored, right? The source talks about these massive carbon sinks, these lockers, where the Earth puts carbon away for a long time.
Nature has these incredible storage lockers. Trees are a short-term one. The ocean is a massive one, holding vastly more carbon than the atmosphere. Rocks, like limestone, are a very long-term one. But the most relevant one for our story today is what happens when ancient plants didn't decay properly.
You're talking about fossil fuels.
I am. And the source material uses a phrase I absolutely love: stored sunlight.
We really need to pause on this concept of stored sunlight because the time scale of this is just mind-bending. The book talks about the Carboniferous period. This was, what, roughly 300 to 360 million years ago?
A completely different world. It's hard to even imagine. The oxygen levels were so high that insects grew to terrifying sizes. You had dragonflies with 2-foot wingspans.
Oh, wow.
But the most important thing about the Carboniferous period is what was happening to the trees.
This was the great era of the swamp forests, right? Ferns the size of trees, just vast marshy jungles.
Right. But here is the biological accident that changed the world. Trees had just evolved a new, incredibly tough chemical compound called lignin. It's the stuff that makes wood hard and bark tough. It was a huge evolutionary advantage. It allowed trees to grow tall and dominate.
But nature hadn't caught up yet. There was a missing piece.
Exactly. There were no microbes, no fungi, no termites that had evolved the enzymes to digest lignin. For millions of years, lignin was basically indestructible. So when these massive trees died and fell into the swamp, they didn't rot.
They just piled up.
They just piled up. For millions of years, layer upon layer of wood holding onto all that carbon it had sucked out of the atmosphere. It was a one-way street for carbon. It was a geological glitch. If those bacteria and fungi had existed back then, that wood would have rotted, the CO2 would have gone back into the air, and we wouldn't have the vast coal seams we have today.
That is absolutely wild. So our entire modern industrial economy, the steam engine, the power plants, everything, is built on a biological backlog from 300 million years ago.
We are, in a very real sense, burning through a battery that took nature 60 million years to charge, simply because some bacteria hadn't figured out how to eat wood yet. And that brings us to the core of the problem. We aren't just releasing carbon, we are releasing ancient carbon that was safely locked away.
We are collapsing geological time into human time.
That is the perfect way to put it. When we burn coal, oil, or natural gas, we are taking millions of years of captured sunlight and captured carbon and releasing it all into the atmosphere in a geological split second. The system, the natural inhale of the plants and oceans, just cannot handle that massive, sudden pulse.
And speaking of plants, it seems we're not helping matters by cutting them down either. The source mentions the slash and burn technique in places like the Amazon.
Deforestation is a devastating double whammy. On one hand, you are removing the very trees, the biological pumps that suck carbon dioxide out of the air. On the other hand, if you then burn them to clear the land, you are immediately releasing all the carbon that was stored in that wood right back into the atmosphere.
There was a statistic in the source that just blew my mind. Every single year, an area of the Amazon rainforest equivalent to 1 million soccer fields is cleared.
1 million. It's a number that's so large it's almost meaningless. It's hard to even visualize that scale. And it's not just for lumber. A lot of that land is cleared for agriculture. Which brings us to some of the more unexpected sources of these greenhouse gases.
Yes, this part was fascinating. It's not just smokestacks and tailpipes. I was surprised by how much our food production system plays a role.
Take cattle ranching. Cows are ruminants. They have these complex stomachs that digest tough grasses through fermentation, and a major byproduct of that is methane.
And they burp it out.
They burp it out constantly. So when you have billions of cattle on the planet for our food system, that adds up to a huge source of methane.
So burping cows are actually a significant driver of climate change.
They are a very significant piece of the methane puzzle. And then you have something like rice paddies.
How does rice contribute?
Well, rice is typically grown in flooded fields, in paddies. That flooded soil creates anaerobic conditions. There's no oxygen, which is a perfect playground for microbes that produce methane as part of their metabolism. The source says that's about 10 to 15% of global methane emissions right there.
And even making cement.
Yes. This one is pure chemistry again. To make cement, you have to start with limestone, which is calcium carbonate. The chemical formula is KCO3.
So the C is carbon.
Exactly. You have to heat that limestone to incredibly high temperatures in a kiln. That chemical process breaks it down into quicklime, which is what you want for the cement, and a byproduct you don't want. pure CO2. It's baked, literally, right into the construction of every city, every road, every bridge on Earth.
Wow. So it really does feel like carbon is just leaking from everywhere in our modern lifestyle.
That is the reality of our carbon culture, as the text calls it. We have built a global civilization that runs fundamentally on combustion.
Okay, so that's the theory. We burn stuff, this gas goes up into the atmosphere, the planet gets hot. But I like to play the skeptic sometimes. How do we know? I mean, how do we really know this is happening? How can we be sure that CO2 is higher now than it was 50 years ago or 50,000 years ago?
That is the most important question, and that brings us to the detective work section of our deep dive. This is the evidence, and it really starts with a man named Charles Keeling.
The Keeling curve. I've seen that graph before.
Right. Back in 1958, Keeling decided to start measuring CO2 levels in the atmosphere with unprecedented precision. But he didn't do it in a city or near a factory. He went to the most remote place he could think of, the middle of the Pacific Ocean to the top of the Mauna Loa volcano in Hawaii.
He wanted the cleanest, most well-mixed air possible.
Exactly. He wanted to measure the background hum of the planet, not the noise of a nearby traffic jam. And what he found was this beautiful, rhythmic pulse. If you look at the Keeling curve graph, it's a jagged line. It goes up and down every single year.
So why does it zigzag like that?
That's the Earth breathing again. Most of the planet's landmass is in the northern hemisphere. So in the northern hemisphere, spring and summer, the vast forests of North America and Eurasia burst into leaf. They suck in enormous amounts of CO2 for photosynthesis.
And the line on the graph goes down.
The line goes down. Then, in the fall and winter, the leaves fall, they decay, and they release that CO2 back into the air, and the line goes up.
That is absolutely fascinating. You can actually see the seasons of the planet in its atmospheric chemistry.
You can. It's the vital sign of a living planet. But, and this is the scary part, while the line zigs and zags with the seasons, the whole thing is shooting relentlessly upward at a 45-degree angle.
What were the numbers again?
In 1958, when he started, the CO2 level was at 315 parts per million. By 2019, when the book was published, it had hit 411 ppm, and it's even higher today.
Okay, so we know for a fact it's gone up dramatically in the last 60-plus years. But 60 years is a blink of an eye for a planet. How do we know this isn't just some natural cycle we don't understand yet? Maybe the dinosaurs had 400 ppm CO2.
A fair question. And to answer that, we have to travel back in time, and we do that with ice.
Ice cores. I love this concept. It's so clever.
It's brilliant. In places like Greenland and Antarctica, it's so cold that the snow that falls never melts. It just piles up year after year, century after century, millennium after millennium. As it gets buried deeper, the pressure compacts the snow into solid ice, and it traps tiny little bubbles of air.
So those bubbles are effectively time capsules of the atmosphere.
Literally. They are perfect, tiny samples of the ancient atmosphere preserved for hundreds of thousands of years, so scientists can drill down, miles down, and pull up these long, continuous cylinders of ice.
Let's talk about the logistics of this, because the source material shows photos of these facilities in Antarctica, and it looks like a sci-fi operation. We aren't just, digging a hole in the snow with a shovel.
No, this is an incredible engineering feat. We are talking about projects like the Epica Dome Sea Core in Antarctica. They drilled down over 3,000 meters. That is nearly 2 miles of solid ice.
And the pressure at that depth must be immense on those little air bubbles.
It is. The text mentions that when they pull these cores up to the surface, these long, clear cylinders of ice, they sometimes crackle and pop as they decompress because those highly pressurized ancient air bubbles are trying to expand.
So walk me through the lab work. You've got this cylinder of ice that you know is from, say, 800,000 years ago. How do you get the data out of it?
You take a section of that core and you melt it very carefully inside a vacuum chamber. As the ice melts, it releases that trapped air that was breathed by mammoths or early hominids, and you capture it. Then you run that air sample through a device called a mass spectrometer, which can tell you the precise chemical composition.
So you're measuring the atmosphere of the past directly. It's not a simulation, it's a physical sample.
It's a direct measurement. It is as close to a time machine as we have.
But the DK guide mentions they don't just measure the CO2, they can also tell what the temperature was. How on earth do you measure the temperature of a day that happened 500,000 years ago from a piece of ice?
That is the cleverest part of all. They look at the water molecules of the ice itself. Specifically, they look at different isotopes of oxygen.
This is the heavy water versus light water concept, right?
Exactly. Most oxygen in water is the standard oxygen-16, which is light. But a very small fraction is a heavier version, an isotope called oxygen-18. When the world is cold, the heavier water molecules are, for lack of a better word, lazy.
Harder to lift.
It's harder for them to evaporate from the ocean, get carried through the atmosphere, and make it all the way to Antarctica to fall as snow. They tend to rain out earlier.
So if you're looking at an ice layer, and it has very little of that heavy oxygen 18.
You know it was a freezing cold era. If you find a layer with more of the heavy oxygen, you know it was a warmer period because more of that heavy water was able to make the long journey. It's a thermometer written in atomic mass.
And when you plot that temperature graph, derived from the water isotopes, against the CO2 graph from the air bubbles,
They lock together perfectly. It's like a key in a lock. For 800,000 years, every time CO2 is high, the temperature is high. Every time CO2 drops, the planet plunges into an ice age. The link is undeniable.
and this incredible record goes back 800,000 years.
800,000 years, and for that entire vast stretch of time, CO2 levels naturally cycled between about 180 parts per million during the depths of the ice ages and about 300 parts per million during the warmest interglacial periods. It never, ever went above 300.
And we are at over 411 in the book, and even higher now.
We are way off the chart. We have completely broken out of the natural ceiling that has governed the planet's climate for almost a million years. That is the smoking gun that proves this isn't just a natural cycle.
But what about other natural cycles? The sun or volcanoes. I've heard people say, oh, it's just solar flares, or one big volcano puts out more carbon than all of human history.
The source material addresses this directly because it's a common talking point, and it's important to clear it up. First, the sun. We have satellites measuring the sun's energy output very precisely. It does vary, yes, with the 11-year sunspot cycle.
But the variation is small.
It's tiny. We're talking fractions of a watt per square meter. It's nowhere near powerful enough to explain the rapid warming we're seeing. In fact, for the last few decades, solar output has been slightly decreasing while temperatures have shot up.
So it's not the sun. What about the volcanoes?
Volcanoes actually tend to cool the Earth in the short term. A big eruption like Pinatubo in 1991 spews out huge amounts of ash and sulfur dioxide into the stratosphere. That stuff forms a haze that reflects sunlight back to space and can cool the planet for a year or two.
But what about their CO2?
All the volcanoes on Earth, on average, release less than 1% of the CO2 that human activities release each year. The idea that one volcano can outdo humanity is a complete myth. The numbers just aren't even close.
Wow. So the volcano excuse really doesn't hold any water.
None at all. The fingerprints on the climate system right now are strictly human.
Okay, this brings us to something that I think is the most alarming part of the entire system. Feedback loops.
Yeah.
Because it's not just that we push the system and it moves a predictable amount. It's that we push it and then the system starts pushing itself.
Exactly. This is where the machinery can start to run away from us. And the classic example we need to talk about is the albedo effect.
Albedo.
Yeah.
That's basically a measure of whiteness, right? How reflective a surface is.
Yes. Think about wearing a black t-shirt versus a white t-shirt on a hot, sunny day. The white shirt reflects the sunlight and keeps you cool. The black shirt absorbs it and you heat up.
So the Arctic ice cap is the Earth's giant white t-shirt.
Precisely. It acts like a giant mirror at the top of the world, bouncing a huge amount of solar radiation straight back out into space before it can warm the planet. But as we warm the planet with greenhouse gases, that ice starts to melt, and it reveals the dark ocean water underneath.
And the dark water is the black t-shirt.
It's the black t-shirt. It's one of the darkest surfaces on the planet, so it absorbs the heat instead of reflecting it, which warms the water,
Which melts more ice.
which reveals more dark water, which absorbs more heat. That is a positive feedback loop, a vicious cycle. The warming starts to feed on itself.
The source mentioned that Arctic sea ice has dwindled by an area 4 times the size of Texas since just 1979. That is a massive loss of our planetary mirror.
It is an enormous change in a very short time. And it's not just the ice. The ocean itself is playing a massive and somewhat hidden role here as a buffer. I don't think people realize just how much work the ocean is doing for us right now.
I read the statistic in the book and it's staggering.
Yeah.
The oceans have absorbed over 90% of the excess heat we've produced since the 1970s.
90%. Just think about that. If the oceans weren't there to act as this colossal heat sink, the atmosphere would be unimaginably hotter than it is right now. We'd be in a much worse situation. But there is a price to pay for that service.
It's not a free lunch.
It's not. Water has a high specific heat capacity. It takes a lot of energy to warm it up. But once it is warm, it holds on to that heat for a very long time. And there's chemical price, too, the CO2 sponge effect.
Right. The oceans don't just absorb heat, they absorb CO2 itself.
About a quarter of all the CO2 we emit gets dissolved into the ocean, but when carbon dioxide dissolves in water, it creates carbonic acid. We are literally chemically acidifying the oceans.
And that is terrible news for any creature that builds a shell.
It's a catastrophe for them. Corals, clams, oysters, even microscopic plankton at the base of the food web, they all pull carbonate ions from the seawater to build their shells and skeletons. But the increasing acidity makes those carbonate ions less available. It's like trying to build a brick house while someone is stealing your bricks.
And we're seeing the results of this already with things like the mass bleaching of the Great Barrier Reef. The book said nearly half of it has died or been severely damaged since 2016 alone.
Yes, that's a combination of heat stress and acidification. It's a 1-2 punch.
That leads us to this concept of tipping points.
Mm-hmm.
The source uses an analogy I thought was really powerful, the idea of ice cubes in a jug.
It's a perfect analogy for what we call nonlinear change. Imagine you have a jug of frozen water at minus 10 degrees Celsius. You start to warm it up, -9, -8, -5. If you look at it visually, nothing seems to be changing. It's still a solid block of ice.
Right, if you were just observing, you might think, oh, this warming doesn't matter, nothing is happening.
Exactly. You could warm it all the way to -1 degree, still ice. But the moment you cross 0 degrees, you hit a physical threshold, a phase change. The entire state of the system fundamentally shifts from solid to liquid, and it happens rapidly.
And the fear is that the climate system has similar thresholds.
That is the great fear, that we might push and push and push, seeing only gradual changes, and then suddenly we cross an invisible line, and a major part of the system, like the Greenland ice sheet or the Amazon rainforest, just collapses or transforms into a new state very quickly.
That is a very sobering thought. It means the past doesn't necessarily predict the future. So let's talk about what happens when some of these lines are crossed, the real-world consequences. We're already seeing them, aren't we?
We absolutely are. This is not a future problem anymore. Let's start with the most direct consequence, rising seas.
Now, you have to clarify something for me that a lot of people get confused about. If the floating sea ice at the North Pole melts, does that raise the sea level? It's like ice cubes melting in a glass of water, right?
You're right, that's a common misconception. And no, it doesn't. That's Archimedes' principle. Floating ice is already in the water, displacing its own weight. If it melts, the water level in the glass stays the same. The real danger comes from land ice.
The huge glaciers and the massive ice sheets that are sitting on top of Greenland and Antarctica.
Correct. When that ice melts or slides off the land and flows into the sea, that is new water being added to the bathtub. That's what raises the level. But there's another equally important factor that accounts for about half of the rise we've seen so far: thermal expansion.
Just the simple fact that water gets bigger as it gets warmer.
Exactly. As the ocean absorbs all that heat we talked about, the water molecules themselves vibrate more, push each other apart, and take up more space. The entire volume of the ocean is literally expanding.
And for a place like Tuvalu, a coral island nation in the Pacific, this isn't a theoretical discussion for the year 2100.
For them, it is an existential crisis right now. Their highest point of land is only about 10 feet above sea level. As the sea rises, salt water is already invading their freshwater lens, killing their crops. They are facing the very real prospect of the total evacuation of their country within a generation.
Imagine that. A whole nation, a whole culture, just erased from the map by rising water. And it's not just small islands. The source brings up the city of Shanghai.
Yes, the Pudong district of Shanghai, one of the biggest financial hubs in the world, is only 10 to 16 feet above sea level. We're not talking about a few villages. We're talking about millions of people and trillions of dollars of infrastructure at risk.
And this water isn't just rising quietly. It's energizing our entire weather system.
It is. Let's talk about the heat waves. The 2019 European heat wave saw Paris hit 108.7 degrees Fahrenheit. I mean, Paris is a city of stone and asphalt. It's not built for that kind of heat. But an even more devastating example was the 2010 Russian heat wave.
That was the one with all the smog and fires, right?
Yes. The heat was so intense and prolonged that it led to an estimated 56,000 deaths. It dried out the vast peat bogs surrounding Moscow, which then caught fire, blanketing the city in a toxic, choking smoke for weeks. It shows how heat, drought, and fire all compound each other. It's a cascade failure of the system.
And then on the other end of the spectrum, you have hurricanes. I always think of warm ocean water as high-octane fuel for storms.
That's exactly what it is. Hurricanes are fundamentally heat engines. They draw their immense power from the heat stored in the warm surface waters of the ocean. The warmer the water, the more fuel is available.
So the storms can become more intense.
More intense, they can carry more moisture, leading to more extreme rainfall. We saw this with Cyclone Idai in Mozambique in 2019. Just biblical amounts of rain and catastrophic flooding, all supercharged by unusually warm waters in the Indian Ocean.
And on the flip side of too much water, you have drought. The before and after satellite photos of Lake Chad in the book are just shocking to look at.
It has shrunk by 90% since the 1960s. That's a water source for tens of millions of people across several countries, and it's just evaporating. It drives famine, it drives conflict over scarce resources. This is why the military often calls climate change a threat multiplier. It takes existing social and political tensions and just pours gasoline on them.
Let's shift gears a little to the direct biological toll, because we are sharing this planet with millions of other species who didn't burn a single lump of coal. And the poster child for this, of course, is the polar bear.
The polar bear is in a really tight evolutionary spot. They are highly specialized hunters. They are designed to live and hunt on sea ice, preying on seals. They can't just switch to hunting on land. They tend to overheat, and there isn't enough high-fat food for them there.
And the text talks about the starvation season.
Yes. In the summer, when the sea ice naturally melts back, the bears are forced to come ashore. They have to live off their fat reserves until the ice freezes again in the autumn. As the world warms, the ice is melting earlier in the spring and freezing later in the fall.
So their hunting season gets shorter, and their starvation season gets longer.
Exactly. And at some point, the math just doesn't work anymore. The bears can't build up enough fat to survive the extended ice-free season. The grim prediction in the source is potential extinction in the wild by the year 2100 if the summer sea ice disappears entirely.
And it's not just the big, charismatic animals like polar bears. The book gets into this concept of phenology, which is all about nature's timing.
This is fascinating and really, really worrying. Nature is a beautifully synchronized ballet. Everything is timed to happen in a specific sequence.
And we're throwing off the rhythm.
We're changing the tempo for some of the dancers, but not others. The book gives this perfect example of European caterpillars and migratory birds. The caterpillar's eggs hatch based on temperature. When spring gets warm, they emerge to eat the fresh new leaves.
Okay, that makes sense. But the birds?
The birds, in this case, pied flycatchers, migrate thousands of miles from Africa. They don't have a long-range weather forecast to tell them what the temperature is like in Europe. Their migration is timed by something more ancient and reliable: day length, the position of the sun.
Ah, I see where this is going.
The world gets warmer, so spring arrives earlier. The caterpillars hatch 2 weeks early. The birds arrive from Africa at the same time they always have, cued by the unchanging length of the days. But by the time they get there and their chicks hatch, the food boom is over. The caterpillars are gone, or they're too big for the chicks to eat.
So the chicks starve. The gears of the entire ecosystem are grinding at a sink.
Precisely. And for some species, it's already too late. The golden toad.
That story is just heartbreaking.
It is. It was only discovered in a tiny high-altitude cloud forest in Costa Rica in 1966. It was this brilliant, vibrant, orange toad. By 1989, it was gone. Extinct.
And what happened in just those 2 decades?
The science points to warmer nights. These cloud forests are supposed to be consistently cool and damp. But as the planet warmed, the nights didn't get as cool, which allowed a deadly chytrid fungus to thrive on the toad's sensitive skin. It just wiped them out. It's widely considered to be the first confirmed extinction directly driven by modern climate change.
So we know where we are. We've seen the evidence for how we got here. What does the future look like? I mean, how do scientists actually model something so complex?
Well, they don't use crystal balls. They use some of the most powerful supercomputers on the planet. They create what are known as global climate models.
These are basically digital twins of the Earth, right? A simulation of the entire planet.
Yes, that's a good way to think of it. They divide the entire globe, the atmosphere, the oceans, the land, the ice, into a 3D grid made of millions of little boxes. In each box, they plug in the fundamental laws of physics and chemistry: how air moves, how heat is transferred, how clouds form, how CO2 traps heat.
And then they run what-if scenarios.
Exactly. What if we keep burning coal at the current rate? What if we aggressively switch to solar and wind? They run these different emission scenarios forward in time to see how the system responds.
And the projections are pretty stark. But there's a crucial concept the book mentioned: committed warming.
Yes. This is so important to understand. What it means is that even if we could magically stop all greenhouse gas emissions today, right now, turn off every car, every power plant, every factory, the warming would continue for decades.
Because of all that heat that's already been stored in the ocean.
It's the inertia of the system. It's like trying to stop a massive freight train. Even after you hit the brakes, it keeps rolling for miles.
Mhm.
The ocean has absorbed so much heat, and it will take a very, very long time for it to slowly release that heat back into the atmosphere and reach a new equilibrium.
And if we don't hit the brakes, if we continue on a high emissions path,
The projections in the source suggest a global average temperature rise of 5.4 degrees Fahrenheit, that's about 3 degrees Celsius, or even more by the year 2100.
now 3 degrees doesn't sound like a lot to most people. I mean, the temperature here changes more than that between morning and afternoon.
That's the weather trap. We have to stop thinking about local weather and start thinking about global average temperature. Let me put it this way. The difference between today's world and the depths of the last ice age, when New York City was buried under a mile of solid ice, is only about 4 or 5 degrees Celsius.
Wow.
So a change of 3 degrees isn't just a slightly hotter summer. It is a geologically significant shift. It means a completely different planet.
So, after all this, what does it all mean? We've looked at the vibrating molecules, the 800,000-year-old ice cores, the plight of the polar bears, the supercomputer models.
I think it means we have to stop thinking of the Earth as an inert rock that we just live on. We have to realize we live inside a machine, a vast, interconnected life support system.
A system where a change in chemistry becomes a change in physics, and that change in physics becomes a change in biology.
Beautifully put. You change the chemistry of the air with more CO2. That changes the physics of the oceans and atmosphere with more heat and expansion. And that, in turn, changes the biology of the entire planet. The extinctions, the migrations, the success of our own farming, it's all one system.
The source material references the Gaia theory at one point, this idea that Earth has been a self-regulating system for billions of years.
It has. It has maintained conditions suitable for life through asteroid impacts, massive volcanic episodes, and changes in the sun's brightness. It has its own feedback loops that keep it stable. But we are currently conducting an unprecedented experiment testing the absolute limits of that self-regulation. We are poking the beast with a very big stick.
It feels like the question isn't really, will the Earth survive? Because the rock itself will be here.
The rock will be fine. Life in some form will almost certainly survive. It's incredibly resilient. The real question is, what kind of Earth will we be living on? Will it be an Earth that can continue to support our global civilization of billions of people, our cities, our agriculture, and the incredible biodiversity we cherish? That is the question that is still being answered.
And it's being answered by the choices we make right now.
Every single day.
If you can, I really urge you to take a look at the visuals in the DK Eyewitness book. Seeing that jagged Keeling curve shooting upwards or the shrinking map of the Arctic ice, it really makes it real. It stops being an abstract buzzword and starts being a mechanism you can actually understand.
Absolutely.
Yeah.
The evidence is there for anyone who is willing to look.
Thanks for diving deep with us today. It's a heavy topic, for sure, but understanding the machine is always the first step to figuring out how to fix it.
Keep asking questions.
We'll see you next time.